So previously we were looking at models for which we could use recurrence relations, and so one of the classic examples that we had was x of n, which represents some quantity at time n, is equal to whatever the previous quantity was at time n minus 1 plus some amount of change. So that change was determined by some rate parameter r, which of course, since it was a rate, would then be multiplied by the quantity at the previous time. So if r was positive, then that would be like the quantity is growing, right? So you had whatever before plus some new amount. Whereas if r were negative, then you'd actually be subtracting from that previous quantity, so the quantity would be decreasing over time. And so we could write this all in a more condensed form as 1 plus r times x of n minus 1. And so this time, if the coefficient is greater than 1, your quantity is growing. If it's less than 1, your quantity is decaying. And we said that this is pretty much like a standard exponential form. And so I guess I'm sort of thinking about this like population growth or population decline, since we're always taking this as the previous amount plus some change, which is either positive or negative. And so when you all did the project with the salmon populations, I think it was in the best case scenario, r was a constant value of about 23%. So let's suppose that your initial population had been 100. It wasn't in the problem I gave you, but let's suppose that we had the population at 100. Things were good, so that this growth rate was pretty reasonable to use. Then no matter what, when we look at one time step later, we should have 123 salmon. So no matter how many times you do the calculation from x of 0 to x of 1, you'll always go from 100 to 123 when you're using this constant r value. But let me go ahead and note that this happens no matter what. But what if, so maybe in year 1, the growth rate was 23%. But then in year 2, maybe the growth was 25%. And then in year 3, maybe the growth rate was, I don't know, only 19% for some reason. And so conditions are still essentially pretty good for the salmon, but just due to natural fluctuations, the growth rate changed a little bit from year to year. And so this brings us to the question of deterministic versus stochastic models. So what I want you to keep in mind is that with deterministic models, the final result for the same initial conditions is always the same. So like I said, if you start with 100 salmon in a deterministic model where your growth rate is 23%, no matter what, after one time step you have 123 salmon. That's not going to change. Whereas with stochastic models, for the same initial conditions, the final result can vary within some range. So in our stochastic model for salmon, if we're allowing the growth rate each year to vary a little bit, then after 5 years, starting at 100 fish in year 0, we may have 162 fish. After 5 years, we may have 200 fish. It's not clear, right? Because it all depends on how R varies each time. But eventually, our hope is that we can figure out what a reasonable range is for that population growth over some amount of time. And so that's where the study of stochastic models comes into play. All right, so a stochastic event, and sometimes people call this a random event, occurs with some probability and this probability is usually determined in one of 3 ways. So it could either be a theoretical probability, so an example here would be like if we flip a fair coin, then we know that the stochastic event of flipping a head on that fair coin is theoretically 1/2, right? If it's a fair coin, there's an equal chance of it landing heads up or tails up. So 1 out of 2 times it should land heads up, 1 out of 2 times it should land tails up. Whether that actually happens is unclear, right? But theoretically, we know what that probability should be. Another way that this is determined would be experimentally. Whoops, what is going on? Still haven't quite figured out why that happens. Okay, so let's suppose that we have a coin. We're not sure if it's fair. So in order to test whether it's fair, maybe we flip the coin a bunch of times to determine what the probability of a heads is. And then the third way, which is related to the second way, I'm having no luck today. Okay, so the third way is empirically, and this is just by observation. So this would be something like when you hear about the probability of getting in a car accident. Well, that's not something that we really have a theoretical sense of how often that should happen, and we surely don't want to determine that experimentally, but we can look at observed data and look at number of car accidents per number of trips taken or something like that and get a good estimate for what that probability likely is. All right, so before we go any further, we need to make a little aside. And that aside is talking about frequency tables and histograms. So let's suppose that you have some sort of stochastic experiment where the outcomes are unknown, and you do this experiment many, many times and record the outcomes that you get each time, and you want to determine how often, again experimentally, or I guess it could be empirically if you're just looking at historical data, how often certain things happen. So one way to quantify this in a really well-organized manner is using a frequency table. So let's suppose that we were surveying a bunch of households just to determine how many people were in the household. So we go to, I don't know, 100, oh no, not 100, let's not do that. We go to 10 households in our neighborhood, and we just knock on the door and say, how many people live here? So the possibilities is that just one person lives there, 2 people could live there, maybe 3, maybe 4, maybe 5. And let's say that in the 10 houses we visit, we don't find a household greater than 5. So across our 10 households, we can come up with how often each outcome occurred. So maybe we found 2 households with just 1 person living there. We found 1 household with only 2. We found 3 households with 3 people. We found, let's see, 3 households with 4 people, and then I suppose just 1 household with 5. So let's make sure that that checks out. So there's 3, 6, 9, 10. Perfect. All right, so this is a frequency table that summarized that data. Since we had only looked at 10 households, it wasn't really that necessary to condense it in this way. But if we had surveyed 1,000 households, then writing it in this form is a little bit more useful than just a bunch of 1, 4, 1, 3, 1, 5, 2, etc. Just a huge list of all of the observations. With this information, we can create what's called a histogram, and this is kind of like a bar chart with a couple of important differences. So a bar or column graph represents categorical data, whereas histograms represent numerical data. And since we're recording the number of people in a household, this is numerical data. Sometimes that's called quantitative data. So I'm going to write down all of the possible outcomes along the horizontal axis. And then on the vertical axis, I'm going to indicate the frequency. Now with histograms, you want to try to make the width of each bar in your graph about the same. When I'm doing it by hand, I can only do that so well, especially with the tablet, so bear with me. So each of the widths is going to be about the same. Let's just say it's width 1. So then the height, or the frequency, is going to be the total number of times that we observed that outcome. So for single households, we saw that happen twice. So let's go ahead and do like a 1, 2, 3 as our scale here. So don't do that. Okay, so we saw a 1 2 times. I draw that bar, shade it in if I like, and I do. 2 people occurred only once. Draw that bar. I am going to shade that in. 3 people, we saw that 3 times. Ooh, and I cannot draw straight lines. Sorry, this is sort of interesting. 4 people also were observed 3 times. And then 5 people, we just saw that once. Alright, so this is my histogram. Like I said, it looks a lot like a bar graph. I said there were 2 important differences. First difference is that we're using quantitative or numerical values along the horizontal axis. So, for instance, our outcome here couldn't be like red hair, brown hair, black hair, etc. That would be a bar graph. Second important difference is that notice how I put the bars right next to each other with no gaps in between. And that's important because in a histogram, since you're representing quantitative data along the horizontal axis, you want to think of this as a number line, right? And number lines are continuous. So if I have a gap between 2 bars, that means that there were no data values recorded for that numerical range, right? So if I had a gap here, that would mean that I did not see a 2-person household. So the gaps are significant in histograms, whereas for bar graphs, usually gaps are included in there just for the aesthetic value. Alright, so that's all that I want for this video. In a minute, you will see some useful distributions for different probabilities. So I will see you in just a minute for that.